today's speaker, Bob West from Stanford University. Bob comes, it's not an amplification mic, it's for the recording. But I will speak more loudly if you can't hear me. So Bob West from Stanford University is our speaker today. He is might be called a computational social scientist. He might be called doing human-centered data science. He actually has a master's from McGill University in computer science before his Stanford Ph.D., which he's in the stages of completing, I believe. And before that, he has a CS undergraduate degree from Munich Technische University. And so his work is at the intersection of network data science, information retrieval, I would say, and navigation, and natural language processing. And I believe he employs very clever techniques to try to experimentally get out navigation behavior, understand how people use data, and not just understand data that's out there, but actually create new data and help figure out how to improve how people understand and use information. I've actually played his Wikispedia game. It's very fun. If you haven't done it, I encourage you to do so. It challenges you to test your navigation skills on a very interesting website that we all know and love, Wikipedia. He's also a co-author on a hugely significant paper, at least to me and those I work with, No Country for Old Members. Very important in the computational linguistics community, as well as the social media, people who study social media and how it's used. One of my favorite papers of recent years, quite an accomplishment. And he's single-handedly been involved with all of the top Silicon Valley companies, I would say, because he has received a fellowship from Hewlett-Packard and Facebook and Wikimedia Research, and he's interned at Yahoo, Google, and Microsoft, so that pretty much covers Silicon Valley. But he's also an academic, having published numerous well-regarded papers, and he's an accomplished teacher, because he's been the head teaching assistant for massive courses at Stanford, including a 300-person course managing 10 other TAs, including a TA for mining of massive data sets and social and information network analysis. And finally, a little known fact, but it's on your webpage, so I think I could state it. Around 2000, you wrote a letter to the editor of Time magazine about an article they had about French culture. And I quote, you said something about Proust too was in search of lost time, not of the lost dime. So we know we've got a very interdisciplinary scholar here today. So let's welcome Bob West to the School of Information.
I was going to say those were my 2 cents, the letter to the editor, but it's more 10 cents, I guess, because it's about a dime. Okay, so thanks for having me. It's great to make that trip across the bay. Human behavior networks. The motivation is that humans live in networks. Life would be hard if we didn't coordinate, communicate, ask each other questions, give each other answers, play games, and all those other fun social things. And over the millennia, our networks have evolved into complex societies of millions and billions of people. And of course, coexisting in those societies wouldn't be possible without at least some level of friction. We agree with some people, we disagree with others, we criticize each other, we form friendships and rivalries, we form groups and parties, all very complex behaviors in our social networks. If we want our societies to run smoothly, then we have to understand such behaviors. Not only people live in networks, but also information and knowledge live in networks. The Encyclopedia Britannica, for example, isn't, or I should probably say wasn't, just a collection of 33,000 pages of plain text. If you really wanted to understand something, you needed to follow cross-references by flipping through a lot of pages. Now, the Britannica has been superseded mostly by Wikipedia, so there's no more page flipping, but now there's link clicking. And the network character of information and knowledge becomes even more explicit in resources such as the Google Knowledge Graph or Freebase Wikidata and so on, resources that are explicitly organized as networks. And the web, finally, is called the web, well, because it's a web-like collection it's a web-like network of interconnected resources. And in all these cases, if you want to understand something, you need to navigate some network. And if we understand how people navigate networks, then we understand better how they understand things, and that lets us help them understand things even better. Now, talking about the web has become, over the last 2 decades, a really important part of our lives. More and more activities are migrating online, dating, shopping, learning, you name it. And in order to given the ubiquity of the web, it's important that we understand and be able to predict the dynamics that are going on in it, because only that way are we able to improve it. And one important observation about about the web is that, on the one hand, it's inherently a computational artifact. In fact, it's the largest computational artifact we've built in history. But on the other hand, it's also a deeply human artifact, because it's mostly humans that contribute the content, and it's also humans that consume the content. So if we're talking about understanding, predicting, and eventually improving the web, it's absolutely crucial that we account for both the computational nature of the web as well as the human behavior that takes place on it. So these are super exciting times for people that are interested in human behavior, such as myself, because all those things that we've always done as humans are now becoming explicitly available. For example, we've always communicated, but now large parts of our conversations are recorded in digital form. We've always voted on each other, evaluated each other. Now we press thumbs up, thumbs down on everything from products to movies, to songs, to people, and this way we record all sorts of even minor decisions. And we've always read, but now we do so by browsing the web, which opens up the opportunity to understand how humans ingest information. In my research, I've been analyzing the digital traces that humans leave behind in networks, such as the web. And this typically involves large data sets up to terabyte and sometimes petabyte scale. And I see it as my task to develop algorithms to turn these data sets into valuable insights, and to then build impactful applications based on those insights. In the process, I've been developing and using techniques from a variety of subfields of computer science and beyond, such as data mining, network science, machine learning, natural language processing, information retrieval, and also human computation. And I guess as an umbrella term, this could be called data science. I recently heard the term data artisan, which I found interesting. Maybe that applies. So here's a more visual map-like overview of my research. I'm broadly interested in the intersection, or maybe more the union, of human behavior, networks, and language. I've tapped into a variety of data sources in that space, some of which I'm depicting here. But to have a coherent theme in this talk, I'll focus on a couple of projects that both deal with Wikipedia as a data set. I've also recently started to collaborate directly with folks at the Wikimedia Foundation, which has given me access to some really nice data sources, such as the complete server logs of Wikipedia. And that has led to some applications, some real-world applications of this research. But I'll talk about that later. OK, so the two projects I will talk about in this talk are, one, network navigation, where we'll ask, how do people navigate networks? And how can we use logs of such navigation in order to make the networks more navigable for the future? In the second part of the talk, we'll look at the interplay between natural language and social network structure, and with the goal of using signals from both language and social networks in order to come up with better models of person-to-person opinions. OK, let's start with network navigation. So we navigate networks all the time. For example, when we browse the web. So here's an example from my own recent past. I had heard that there had been some groundbreaking progress in the field of graph isomorphism. And I wanted to learn more about that. So I typed my query into the search engine. And by clicking the first search result, that was really like parachuting onto this complex network of interlinked pages. But from there on, I was really on my own. And I kind of had to fight my way through the thicket by foot by clicking manually from page to page until I finally found the paper that I was looking for. And the point I'm making here is that using the search engine alone didn't cut it. I really had to navigate because I didn't know the title nor the author of the paper that I was looking for. So why should we study network navigation? Well, as the example I just showed attempted to show, it's quite a hard task for humans. But if we understand how humans do it, then that puts us in a position where we can build tools and applications to make it easier for them to find what they're looking for. For example, if we could predict the user's information need after seeing just a few initial clicks, or if we could even navigate automatically, then that would make it easier to supply to the user the information they're looking for. Or if we could determine if a user is lost during their navigation, then we could proactively offer them help. And finally, if we could automatically improve the hyperlink structure of a website, then that would also make it easier for users to find what they're looking for. So during my PhD, I've worked on all of these questions, but in this talk, we'll focus on the last item, improving website hyperlink structure. I think I don't have to convince you that hyperlinks are really important on the web. They're kind of really what makes the web the web. But it can also be, and here when I say good hyperlinks, I mean hyperlinks that let the user find what they're looking for effectively. It's also hard, though, to find to maintain a good hyperlink structure on a website. And as an example, let's look at Wikipedia. English Wikipedia has 5 million articles, but every single day, 1,000 new articles are created. And if those articles aren't tied into the rest of the article network properly, then it will be really hard for users to discover them, and the articles will remain largely useless because they're invisible. At the same time, there are only about 12,000 active editors on Wikipedia at any time. So you see how there's a mismatch between the work that needs to be done and the work that can be done by the available workforce. Plus, we found empirically that the links that people do add, that editors do add, are oftentimes not very useful. We find that 2/3 of all human-added links, so all the links that are added by human editors within 1 month, aren't even used a single time in the entire month after the link was added. So it's clear that there is a need for automated methods to support humans in improving the hyperlink structure. And given the importance of the task, it's not surprising that there's been a bunch of work on it. But one thing that all of the previous, or most of the previous approaches have in common is that they tend to be based on the graph structure only. So one typically heuristic would be triangle closing, which says that if you have two pages that already have a lot of common neighbors, then you should also add a direct link between those. And to give you a feel for how that heuristic could go wrong, let me draw a quick analogy here. Imagine that you're a civil engineer and your task is to improve the US road network. Now, if you followed a purely structure-based approach, then you might say, aha, there are these two places in Nevada and Idaho. If I added a direct road between those, then I would close a lot of triangles, which is a good thing to do. But if you did that, you would ignore the fact that in that area there's overall very little traffic. So you would end up adding a road that would not be used by many citizens. So you'd basically be using taxpayer money. You don't want to do that. What you'd really want to do is take the traffic into account and build those roads that would benefit the largest number of citizens. And I argue that when we talk about building hyperlinks rather than building roads, we should also build those hyperlinks that would benefit the largest number of web users. So that's desideratum 1 for a link recommendation method. We should account for human usage. And such automated methods can easily generate thousands or even millions of good recommendations. But as we saw, there is only a limited workforce that can actually take those recommendations and put them into the site. For example, on Wikipedia, there needs to be a human in the loop who actually adds the link. So we don't want to create more work than can be done by humans, and that gives rise to desideratum 2, which is don't overwhelm human editors with more work than they can do. Okay, so let's start with desideratum 1. How can we account for human usage when recommending links? We start from the very simple premise that a link is useful if it's used. If a link is never clicked, then from the user's perspective, it might not just as well not be there in the first place. And initially then, every pair of pages that's not linked yet is a candidate for a potential link. And to capture the quality of a candidate, we then want to predict how often a link from a source S to a target T would be clicked if it were added to the site. And here's a very simple formula for that. So the number of clicks that a link from S to T receives can be decomposed into the number of times that the source of the link is visited times the probability of clicking through to the target, given that the user is in the source. And I call that probability the click-through rate. Now that first quantity, the number of times the source is visited, can simply be counted in the logs. So that's easy. That's not possible, however, for the second quantity, for the click-through rate, because the link doesn't even exist yet. So we can't count how often it is clicked. So the task then is to instead predict the click-through rate of a link before the link is even introduced. Here's the intuition behind our approach to predicting click-through rates. Imagine that there's a pair of pages, S and T, and there's no direct link between them yet. But also imagine that users who visit the source page S really have a desire to also learn about T. Now, if they really have that desire, then they will still find some way of learning about T. For example, by navigating on indirect paths, or by briefly leaving the site, going to a search engine, searching for T, and then coming back to the site. And you can also model that as an indirect path through the search engine. And now, when that direct link is added, there is in principle no more need to take an indirect route, because you can just take the direct link instead. And in the most extreme case, all the click volume that used to flow over indirect paths would now be redirected over the direct pipe. Okay, and that would give rise to this simple model where we would say the probability of taking the direct link after it's added can be approximated as the probability of taking an indirect route between S and T before the direct link was added. Now you might say that's clearly not fully realistic, because even with the direct link there, people can and people still will take indirect routes. And that's right. But to convince you that this might be good enough, let me show you a brief result. A good thing with Wikipedia is that the complete edit history is public. So for every link that's in Wikipedia, we can exactly figure out when it was added. So what we do is we take a bunch of links that were added at some within a month, and then we can estimate the click-through rate based on the data before. That's our estimator, and we can calculate the ground truth after the link was added. And that's what you'll see on the scatter plot. You'll see on the x-axis the estimate, and on the y-axis you see the ground truth. So perfect performance would lie along this diagonal. And while obviously we don't get perfect performance because we're reasoning here about humans, which are inherently hard to predict, you can see by the elongated shape of that point cloud that there's clear correlation there. So we have a Spearman rank correlation of 0.64. So although the method is very approximate and very simple, it gives sufficient results. Okay, so now we have all the ingredients necessary for predicting the number of clicks a link would receive, even based on data before it's added. And what you would do then is to simply rank all candidates by this estimated number of clicks, and you would then pick the top K and recommend those to editors. Why the top K? Well, that's desideratum 2. We don't want to overwhelm the users with more work than they can do, and K is basically a parameter that captures the amount of work that can be done by the workforce that you have. And now, for the sake of argument, imagine that all K recommended links point out of the same source page. So that would be this scenario here at the bottom right. There's a single source page S, and all your K links would point out of that. Would that be a problem for us, or would that be okay? Well, it turns out that that would be a problem because links aren't independent. Empirically, we found that if you add more and more links, all pointing out of the same source, then that will not entail that users will also make more clicks out of that page. Instead, users have a limited amount of attention that they can spend on clicking links, and all the links compete for that limited attention. So for us, that means, as a rule, that we should not add too many outlinks out of the same source page S, but that we should instead spread the links more evenly over the entire network. So that means that to make good recommendations, we should somehow account for the user's limited attention. And one straightforward way of doing that is to assume that the user has the attention to click exactly one link from every page that they visit. The other scenario would be that the user opens several links, say in background tabs or something like that. But this assumption that the user can make exactly one click would then lead to navigation traces that are forward chains. And we find empirically in the data, and this is again Wikipedia browsing logs, that 93% of all navigation traces are such forward chains where the user makes exactly one click from every visited page. So this is actually a realistic model. And now, given that our goal is to add links that will receive a lot of clicks, that will benefit a lot of users, the natural objective function is this. Given a set of new links A that we want to add to the site, what is the total click volume that those links would receive under this chain model? And I call this f of A, where A is a set of links. Okay, and there's a simple way of writing down this objective function in terms of quantities that we already have. So these probabilities that you see here are the individual click-through rates that we've estimated via indirect paths. I've just shown you how we can do that. And then this ratio here is basically normalizing all the links that point out of the same source such that their probability sum to 1. That enforces that the user paths become chains. And then by forming this expectation over all the sources, we compute the click volume that flows out of all the pages in the network. Okay, so one nice property that this objective function has is what's called diminishing returns. What I mean by that is the following. Every new link that you add to the network increases the value of this objective function by some marginal amount. It increases the total click volume over the new links by some amount. But as you have already added more and more links to the network, the marginal amount that is added to the objective function becomes smaller and smaller. So it can be shown formally based on this formulation, but the intuition is that links compete for attention, so it's not possible to just increase that quantity indefinitely. There's competition between the links, and that leads to diminishing returns. And what that means for us is that it provides a natural incentive to spread the links over many source pages rather than over-optimize a single source page, which is exactly what we want. Okay, so now the only thing that's left to do is to come up with an algorithm that maximizes this objective function. That is, that finds a set of candidates, of links to add to the site such that their total click volume is maximized. And note that what we're maximizing over is the set of all subsets of candidates, which is exponential in the number of candidates that we have. So clearly we can't do an exhaustive search. We need to do something smarter. And luckily, this greedy algorithm that I'm going to present to you now does the job. And to understand this algorithm, let's start with a scenario where there's only a single source page, S1. And this source page will have a set of existing links that point out of it. That's what you see in gray here. And there's also a set of candidates. Those are new links that you could add out of pointing out of S1. And the numbers on the edges capture the click-through rates that are estimated via indirect paths. Okay, so now if I ask you to pick the top K links out of those to maximize the overall click volume over those links under this chain model that I just introduced, then the best you can do is to simply sort those candidates by click-through rate and then pick the top K greedily. Okay, and you can then also compute those marginal gains. That's as I said before, every link that you add to the solution will increase the value of the objective function by some amount, and that amount is called the marginal gain. And you can simply compute that by iterating once over the ordered list. Okay, now you can do that same thing for every source separately. And the crucial observation now is that if once you consider multiple sources, then the marginal gains are kind of independent of each other. What I mean by that is that if you add a blue link to your solution, that will not change the marginal gains of the yellow link. And that's because our objective function decomposes into a sum of all these sources. Now, what that means is to get a global list of marginal gains, you can simply merge all those local lists into one big one, and then greedily pick the top k from that global list, and that's the global optimal solution. So in a nutshell, that means that greedy marginal gain selection gives the globally optimal solution for this problem, which is nice because it's very, very efficient once we run it on large data sets. And that's actually what we're going to do next. So we want to see how this does in practice. So, and the goal is to make Wikipedia more navigable by adding hyperlinks to it. And what's nice here is that we have the complete navigation logs, so the complete server logs from Wikipedia. Every time someone loads a Wikipedia page on the planet, this is recorded in those server logs. And through a collaboration with the Wikimedia Foundation, I have access to that data, and it's actually quite a lot of it. So it's about 14 terabytes of raw logs per month. And we have 3 months of logs here in this study, January, February, March. And the setup is the following. In the first month, we collect the navigation traces, and those we feed to the algorithm that I just presented. And then the algorithm will spit out the top link recommendations that we would add to the site, but we don't add them to the site. We just keep them for ourselves, and then we wait for 1 month, and we see what Wikipedia editors do naturally. So during that 1 month, humans that have nothing to do with our research will just do their regular Wikipedia editing work, and they add 800,000 links to Wikipedia in that month. And then in the 3rd month, we can evaluate. We can ask how many of the links that we would have recommended were naturally, organically added by Wikipedia editors, and second, how many clicks were made on those links. Okay, so here's the answer to the first question. How many of our top K links were added independently by human editors? What you see here on this plot is on the x-axis, the size of the solution. So that's the number of recommendations that we're allowed to make. And then on the y-axis, you see precision at K. That's what fraction of our recommendations was added independently by humans. And so, for example, when we make 1,000 recommendations, then about 60% of those are added independently by human editors, which is quite a large number. So this is a first indicator that, that our method does something good. Now, we also eyeballed a lot of the remaining 40%, and those intuitively tend to be good suggestions as well. They just never happen to be added by humans, which is kind of good because it means that our method can suggest things that would not have otherwise been done later by humans anyways. Okay, recall though that what we're really after is to add these high impact links, so links that will benefit a lot of people. And that's what this, this next plot is measuring. So on the x-axis here, you see the same quantity, size of the solution, the number of recommendations that we make. And the y-axis now, you see the average number of clicks that each of our K-recommended links receives within the month of March. And we compare this to the human baseline. So that's the average number, that's the number of clicks that the average human added links receive. You see that, that's pretty low, that's about 8. So on average, a human added receives only 8 clicks per month. And the recommendations that our method makes are significantly better. For example, if we take K equals 1,000 again, then each of our top 1,000 recommendations receives about 120 clicks in a month. So for K equals 1,000, that's an increase of 15 over the human baseline. Put differently, that means that by adding 1,000 links to Wikipedia, we could improve the experience of 120,000 users, assuming that each link click is made by a different user, which is close to what's actually happening. Okay, so these results are quite promising, so we don't want to stop where the paper stops, but want to have some real impact. And therefore, we designed an easy way of turning our recommendations into real Wikipedia links by developing a plugin for the Wikipedia editing tool. So what you see here is a screenshot of Wikipedia's so-called visual editor. So you notice all the edit buttons up there. So this is actually the view when you want to edit the article. It's like a WYSIWYG editor for Wikipedia articles. And by the way, can anyone guess which article this is? By looking at the hands, maybe beautiful hands. Mona Lisa, yeah. So our method has determined here the best new links to add out of the Wikipedia article about Mona Lisa, and it has also identified good positions in the article where to add those links. Now, I didn't talk about how that's done, so you just have to believe me that that is possible. And now the human editor is walked through our suggestions one by one and is asked whether they think that that link should be added at the given location in the page. And then if they think so, then they just click add link and the link gets added. So that vastly decreases the cognitive load on the editors compared to someone having to just screen that entire source code, which is much more complex. And so this link, for example, Gherardini family, is definitely useful because Mona Lisa, the real person, stemmed from that family. Okay, so that might be a good time to ask intermediate questions because I'm going to switch to another project after this. Yes?
When you say add links, do you just mean link to an existing page or do you mean create the page?
Yeah. So here I'm talking about links to existing pages. In another project, I worked on finding missing pages, but that's separate. Yes. This, yeah.
The one where you had the average.
Oh yeah, of course.
I was curious, are you evaluating the actual number of click-throughs based on links that the algorithm recommended adding and that were also added by human editors?
Yes, good point.
Okay, so kind of what this graph might be saying is that if the algorithm thinks it's a good link to add and the human editor also independently thought it was a good link to add,
Exactly.
then it tends to
Yes. Yeah, so this is kind of reordering the things that were added by humans. You can draw a different plot that would also count those links that were not added by humans, and you can count those as receiving 0 clicks. Yeah. And then you get a similar curve. It's obviously going to go a bit lower, but it's still then at 1,000, instead of 120, you get 90 then. So it's still, the results still kind of hold.
So you're saying even if you weren't evaluating the algorithm recommended links that were not added by humans. These are only ones that
But that's the thing I just talked about would be that. So if something got recommended by the article but never got added by human, then you can count that as receiving 0 clicks. Yeah. And so that will lower the average, but not by too much.
Okay, cool. And then this seems to be like assuming that like we want to shorten the path from where the user started to where they want to get to. And I think that's true in many cases. But then you look at cases where like maybe that wandering.
Yeah. That's an interesting case, and it's actually relevant because there has been literature that showed that what's called the scenic route is sometimes relevant. There might be additional information that you kind of pick up on the intermediate articles between the start and the target. So that's definitely relevant. We're now doing follow-up work that's looking more from a user. More from an HCI perspective, what do people actually want to get out of their navigation traces? Collecting labels for traces now that tell us explicitly whether people just want to look up a quick fact or whether they want to learn about a topic from the bottom up. And I think if they want to learn from the bottom up, then those intermediate steps might actually be important because they're adding additional information. So this is definitely interesting for future work.
Can I just follow up on that? So there may not be there's one optimal solution according to your algorithm, but there may be many different preferences for human searching. So you might find the bottom-up approach yields multiple different approaches. So then, I may, in different searches, want to look for prefer different routes, or for different projects. How do you address that?
Well, so yeah, this is more of a kind of wisdom of the crowds approach, right? If it's what the majority of people wants. But again, I think this follow-up research that we're engaging in now, where we're analyzing what are the individual information needs of people, that will get way more in that direction because we can then basically partition the group of users into people that have different types of information needs and thus expose different behaviors, and will allow, I think, for much more fine-grained methods than this.
For future questions, if you could raise your hand, I'll bring you the mic. It's for our online audience. It's not for sound amplification, just so they can hear.
And we can come back to this also at the end of the talk, so no need to ask all the questions now. Okay, then I'll just move on, I guess, to the second part, which is on person-to-person opinions in social networks. So in about 30 minutes from now, I'll be done talking, and you'll have opinions about my talk. So some might have liked my talk, some might have kind of liked it, and some might be more snarky and sarcastic about it. But regardless of what your opinion is, it doesn't make sense to form to voice such an opinion in a vacuum. Opinions are always formed in the context of a social network. And so since both language and network are involved in such opinions, I will argue that we should model and reason about person-to-person opinions jointly in terms of both the language that expresses the opinion and the social network in which the opinion is formed. And that's what the second part of the talk is going to be about. So first of all, though, why should we study person-to-person opinions as scientists? And well, the first thing is that they're actually quite prevalent. By some accounts, 2/3 of all the words that come out of our mouths are gossip, broadly construed. That is, talk about our social network, about other people. The reason probably being that reputations play a really crucial role in society. For example, in politics, endorsements, accusations, assessments really have the potential to sway public opinion. You could even say that one of the main jobs of politicians is to have opinions about other politicians. You definitely see that currently in the tragedy of Trump versus Cruz, for example. So the applications of models of person-to-person opinions are obvious. For example, if we could model opinions between Congress people, if we could understand better, then that would help us understand better how decisions are made at the very highest level of society, or presidential candidates currently. Or to stay true to this theme of Wikipedia, if we could detect and diffuse conflicts between Wikipedia editors before they escalate, then that would help make for a much smoother experience in that community. As I said, we're interested in opinion models that take both language and social networks into account. So a natural way forward is to model the social network as a signed graph, as is usually done. So here, the nodes of this network would correspond to people, and edges between the people would correspond to who knows whom. And we also assume that there is text associated with the edges. That could be, for example, the messages that are exchanged between those two people. And we assume that there is also a sign associated with each edge. So a plus would mean that the two people are friends, minus that they are foes. Or a plus could also mean that they trust each other, minus that they distrust each other, and so on. And crucially, we assume here that the signs are only partially observed. That means that for some pairs of people, we don't know whether they're friends or foes. And the task then is to predict the signs of the unobserved edges based on 1, the signs of the observed edges, and 2, the text that's associated with the edges. Okay, so there are some typical approaches of tackling that problem. Here's the typical natural language processing approach. This approach would ignore the network structure and would frame the task as one of text classification, where the input would be engrams or words extracted from the messages, and the output would be plus or minus, capturing whether this is a positive or a negative sentiment expressed in the message. And then you could throw this into your favorite classifiers, such as logistic regression, support vector machine, naive Bayes, and so on. And in this setup, then you would train the classifier based on the observed edge signs with the text, and the task would be to predict the signs of the remaining edges with that model. Okay, and the idea is that the model would pick up on things like amazing is typically a positive word, so if that word appears, then it boosts the score. And sick might be typically a negative word, but sometimes also a positive one, and then you would learn weights for these words. Okay, a very different approach is the social network approach, which would ignore the text and reason exclusively about the structure of the networks by applying these intuitive social rules, such as a friend of my friend is my friend, a friend of my enemy is my enemy, or an enemy of my enemy is my friend. In the language of graphs, these are statements about triangles of nodes. For example, a friend of my friend is my friend corresponds to a triangle that has all positive edges. An enemy of my enemy is my friend corresponds to a triangle that has 2 negative edges and 1 positive edge. In fact, there are 4 types of signed triangles overall, with 0, 1, 2, or 3 negative signs. And there's actually an entire theory about these triangles in sociology that goes back all the way to the 40s, and that's called structural balance theory. And this theory predicts that some of these triangle types are much more common than others. And in fact, it says that the upper 2 types here will be common. So that means 0 or 2 negative signs will be common, whereas the other 2 triangles will be much rarer. Why is that? It's, so if we take, for example, the lower left example here, that's a triangle that has plus, plus, minus. So the top person here would have 2 friends that are mutual enemies. And then the theory predicts that this is something that's going to be rare because those 2 bottom people have an incentive to also become friends because they're going to hang out with the top person all the time. Okay, so how can we operationalize this to make predictions about unknown edges? For say that you want to predict the sign of this edge here with the question mark, and then you observe that it's embedded in a triangle that already has 2 negative signs. And then you would look up basically in your little table here, you would see, aha, if we have 2 negative signs known, then the 3rd edge should be positive. An enemy of my enemy is my friend. So you would predict a positive sign here. Okay, so both the natural language processing approach and the social network approach leverage useful signals. And our contribution is a unified approach that leverages both types of signal jointly. But before I show you the model, let me briefly motivate why this is a useful thing to do. Imagine that we have this little toy network here of 4 nodes, and you want to predict the sign of that gray edge in the middle with the question mark. Okay, so the text associated with that edge is "that was sick." So if you just look at the words, then your language-only model might have learned that sick is typically a negatively connotated word. So it might say this should be a negative sign. However, if you look at the network context, then you see that the edge is embedded in 2 triangles. One of them has 2 positive signs. The other one has 2 negative signs. And in both of these cases, the structural balance theory predicts a positive sign. So in this case, taking the network context into account would help you basically detect the non-literal tone of that message here. Okay, so here are more details about how we go about solving this. So we start with a text-only model. That's basically the NLP approach that I outlined earlier, such as a logistic regression, for example, where you would take only the words as input, and the task is to predict the sign of the message, positive or negative. Now, this gives you a text-based sentiment prediction, which is basically a probability that the edge is positive. Okay, and now the objective is to predict the signs of the unobserved edges such that, 1, you stay close to the predictions that come from the text only, and 2, you create triangles that are in line with the predictions of structural balance theory, such as a friend of my friend is my friend, and so on. Now, obviously, reconciling these two objectives is not always possible. Look at this example up here. You have this little triangle. The text says "you're a fool." So clearly, this is a negative message, but the network context predicts a positive sign because a friend of my friend is my friend. So there's really a trade-off, and we need to that we need to find. And we find that trade-off by combining the 2 signals into a combined cost term that looks like this. It takes account of takes both of these into account. There's an edge cost and a triangle cost. The edge cost measures how much you deviate from the predictions that are made by the text only, and the triangle cost in simplified terms, counts how many triangles you create that disagree with structural balance theory. And then the 2 of them are traded off by this lambda parameter that can be learned from data in a machine learning fashion. Actually, there's a bunch of machine learning behind this, but I'm not going to make this the focus of this talk, but I'm happy to talk about it later. Okay, so this objective function kind of really captures what we want to capture, the trade-off between edge and triangle costs, but there's a catch, as so often. Minimizing this objective function can be shown to be NP-hard. So it's not feasible to do it exactly. And we can show that with this cute reduction from a spin glass problem. But I don't want to obsess on the bad news here, but instead highlight that there is a solution. And as so often, the solution is to relax. And in this case, it's to relax the problem to a continuous form. So here's what I mean by that. The original formulation of the problem is binary, meaning that edge signs can only be negative or positive, which corresponds to 0 or 1 in the way I wrote it down here. But nothing keeps us from relaxing that constraint and allowing for edge signs also between 0 and 1. So then an edge sign of, say, 0.8 would mean that there is an 80% chance that this edge is positive. And now what's nice when we relax this is that it can be shown that this formulation is equivalent to what's called a hinge loss Markov random field, which is a type of probabilistic graphical model. And again, I'm not going to go into the details here, but the punchline is that the problem then isn't NP-hard anymore, but that it's a convex numerical problem. And we all know what that means. It's good news because there are scalable algorithms for finding the exact optimal solution for those. Okay, so let's look how well this does in practice. And to stay true to the theme of this talk, I'm going to show the evaluation that uses Wikipedia. The goal here is to predict the outcome of Wikipedia adminship elections. The background is, say I want to become a Wikipedia administrator, then I would run for election, and every other Wikipedia member could cast their vote on me. They could say, do they support or oppose me? And they would also leave a short textual snippet that justifies why they voted one way or the other. So here you see some example. On the top, there are some support messages, polite and helpful and things like that. And at the bottom, there are oppose messages, things like not yet ready and so on. And what we do now is we hide a fraction of the edge signs. So first of all, we really have a network here now of users voting on each other and text associated with those votes. And we hide a fraction of those edge signs. And the task is to predict what those edge signs are based on the observed edge signs and on the text. And we evaluate this in terms of area under the ROC curve because it's basically a binary classification task, plus or minus. And that's what you see on the y-axis here. Please ignore the x-axis for now. I'm going to talk about that in a second. Just looking at the y-axis, we evaluate 3 methods. We evaluate our combined method in black, language plus network signals, and we evaluate the 2 separate methods, language only and network only. And we see that the combined method in black does better than each of the separate methods, which is good news. But we also see that the language only model already does very well. It has an AUC of nearly 90%. And so there isn't much that you can improve upon. But that's really a peculiarity of the Wikipedia data set, where the language signal just happens to be really strong. This might not be the case with all data sets. And what's worse, you might not know ahead of time whether the language signal or the network signal is stronger with a given data set. So what we want to do now is we want to see how does our method fare if the language signal becomes weaker and weaker. And the way I do this is by basically mutilating the language signal in a controlled way by dropping the most informative words from the messages. So what I do is I compute for every word separately how predictive is it of the edge sign, and then I rank all the words in that order, and I drop the top X words from the text. And that's what you see on the x-axis. So as you go further on the right, the textual signal, the language signal, becomes weaker and weaker. So you see that the orange curve is going towards random. So there's more and more noise in the language. The blue line, that's the network signal, stays the same because it doesn't use the language at all. And what's crucial is that the combined model never gets worse than the language-only model. Okay, so that means even as the language becomes worse and worse, the method learns to default back to the other type of signal. So our method is adaptive in that sense. Okay, good. Are there any questions about this before I move to ideas for future work? Okay, so we can, as I said, we can also have such questions at the end. Okay, so I think that thinking about the future, this crossroads of human behavior, networks, and language is really rich hunting ground for a lot of interesting and also high impact research. And I have a lot of ideas, but here are just a few that really fascinate me and that kind of come out that connect directly to what I presented previously. So you might have noticed that I'm quite passionate about Wikipedia, which is true, but I also think that there's a lot to be improved about Wikipedia. It nearly has this 20th century feel to it, although it's actually a product of the 21st century. But I think that through my collaboration with the Wikimedia Foundation, I think I'm in a really good position to think about the next generation of knowledge networks, because I have this conduit to those people there, and they're really willing to experiment with new ideas. So one big question is about user needs, and we touched on that earlier briefly. No one really knows what people who come to Wikipedia really want to get out of it. Even the people at the Wikimedia Foundation don't know, and I talk to those people a lot. So is it that people want to just look up quick facts and definitions? Do they want to do their homework? Do they want to learn about something from the bottom up? Or do they just explore randomly? I do that a lot. Probably people do all of that, but if we could figure out what one specific user wants to get out of Wikipedia at one specific time, then that would put us in a position to cater to the user's information need in a much better way. So for example, if we could figure out that a user has a long-term educational need, they really want to learn about something from the ground up, then we could propose to them a curriculum of articles to read where one article gently builds on the next and would lead the user to an understanding of the topic in an efficient way. And I think that such curricula could also be mined from navigation traces. And I have a lot of other ideas, but I need to come to an end soon, so let me just briefly mention something that's basically going on right now in this space that we're doing right now with the Wikimedia Foundation. Just recently, we designed this survey where we're asking users to tell us what their information need is when they look at one specific page. And we ran this actually for an entire week on 2% of the entire reading population of Wikipedia. So we've collected a lot of these responses. And what's nice is we also have the navigation traces that people took before they answered that question. And now we can use this label basically in order to build predictive models to look at just the first few clicks that people take and then to predict what's the information need of the user. And then possibly adapt the user interface to make it easier for the user to meet that information need. I think there was a question there. I think, I'm not positive, but I think it's in the single digits. It's single-digit %, yeah. It still gave us tens of thousands, I think hundreds of thousands of answers. Okay, so I talked a bunch about Wikipedia, but Wikipedia is really just one player in a huge landscape of media outlets on the web, and they're all connected. They all cite each other, they influence each other, they contradict each other, they agree with each other, and so on. And I think that studying these networks and the language that flows over them poses a lot of interesting research questions. For example, what's the interplay between the propagation of a piece of information and the language that it contains? In the case of false information, how do I have to disguise a lie in order to make it spread as fast and far in the network as possible? Now that's really crucial to understand, because if we understand how lies behave, then that also makes it easier to catch them before they do too much damage. There are also many interesting aspects of media language that I'm really interested in. For example, political correctness. What's okay to say today might not be okay to say tomorrow. What are the social processes that make us somehow collectively agree on what things are okay to say, and can we predict what will become a norm? Another super fascinating question, I think, is that of collective memory. How do we as a society collectively remember people, events, and so on? And how is that influenced by the media? And how do we influence each other in that respect? I've started to dip my toe into the water with respect to that question of collective memory by starting to work with a large corpus, it's many, many terabytes, of news and social media in order to understand how media coverage of famous people changes as those people die. So how do we collectively remember people after their death? And I think these are really fascinating questions. I've been working mostly with linguists on those, but I think it would be very fascinating to also bring in other social scientists and people from journalism studies and history also to take a closer look at such questions. And finally, earlier I presented a way to use both textual as well as network features to model opinions. And network features are useful because they capture the social context in which an opinion is formed and uttered. For example, and sometimes this context is absolutely crucial and necessary in order to understand an opinion. For example, this guy says exactly the opposite of what he means. He says great talk, but he really means bad talk. So he's being sarcastic or ironic. And in the future, I want to build on the ideas that I presented earlier to use text and the network context together in order to model and detect non-literal language, such as irony, sarcasm, and humor. I think these will be really crucial components for smarter text mining applications that can recognize such ways of non-literal speaking, but also for truly intelligent user interfaces that really understand what a user wants. If we are ever to communicate with a user interface in a natural way, then that user interface will have to understand things like sarcasm and humor. I'm particularly interested in computational aspects of humor. So for example, I'm a big fan of The Onion. I read it nearly every day. And every time I read such a headline, I'm thinking, wouldn't it be great if we could generate such headlines automatically? And obviously, that's a really hard task. And I might not see computers that are truly humorous in my entire life. But I think that because I think that humor is kind of AI complete, we need to solve nearly all of AI in order to solve humor. But if we take the problem of humor head on, I think we can make a lot of progress towards smarter AI and user interfaces. So in this specifically here, one observation is that these satirical headlines from The Onion are typically very similar to real news headlines from real news outlets. That's part of what makes them funny. So the idea came up to treat the task of creating these funny headlines as a task of machine translation. But instead of translating English to French, the task would be to translate something from serious to funny. And now machine translation works because we have those large aligned corpora where we have sentences in English and in French lined up. They say the same things. So it seems to me that it would be really useful to have a corpus that also aligns serious and very similar but funny versions of the same statement. But such a corpus doesn't exist yet. So I wanted to create such a corpus. And the first idea was, can we give serious headlines to people and ask them to make a minimal change to turn them into something satirical? Now, it turns out that's really, really hard. You need some proper talent for it, and I definitely didn't have it. I tried for hours, and I just couldn't do it. Now, the opposite turns out is much easier. If you take something that's already funny and you destroy the humor in it to make it serious, then you still get a pair of serious and funny, but it's much easier to do that. And so that idea we actually turned into a human computation game that was done during an internship with Microsoft. You can imagine that my fellow interns were quite jealous when they saw me reading like Onion articles all day long and getting paid $8,000 per month for it. But it worked. And so we created this game, Unfun, where the player gets a headline from The Onion, satirical headline, and the task is to make a minimal change to it in order to fool other players into believing that the headline came from a real newspaper. So for example, here, you could change this headline, Margaret Thatcher's ashes scattered over free market, into Margaret Thatcher's ashes scattered over Atlantic Ocean. So you just have to replace 2 words, and you have a pair of serious and funny. And now, why do I say this in the future work section if the game already exists? Well, because the really hard and the really interesting task is yet to follow, namely to use that data in order to automate the task and translate serious into funny things. And I think that a more viable approach is actually to come up with a system where humans and computers collaborate in order to create humor, because some things are easier for humans and some things are easier for computers. So stringing the two together in a smart way, I think, might be a way of doing this. And as I said, it's not only a fun project, but I do think that addressing the problem of humor is really important for anything that even gets close to proper AI. Okay, so on that note, let me thank you, and also thanks to my collaborators.
Thank you. In terms of future work, on your network study, you looked at triad structural balance theory. But social network research has long gone to complete networks. So they would look at centrality measures in terms of influencing others and peers in a network. So have you considered adding those kinds of measures, which might complicate your analysis if you move from the triad to the complete network and using concepts like centrality in your modeling of how to predict the linkages?
Yeah, so there are, first of all, there are interesting connections between the global network case and the local case that I talked about, the triadic case. So there are theorems that show that a network that's balanced at the global scale, so basically a network that you can pull apart into 2 factions, and everything, all the edges within a group are positive, and all the edges between the groups are negative. So if you can do that, then also all the triangles will be balanced. So there are these nice connections between the two. But I see what you're saying. You're saying that we could use additional features maybe that could make a stronger analysis. There might be different types of people. Someone who's very central in the network, it might be more important to have a positive connection with that person, for example, I guess. That would be my intuition. And so I haven't used and thought deeply about this yet, but the framework that we have would allow for incorporating such things, because it's a machine learning framework where you can stick in features, and nothing would keep us from also add a feature that captures the centrality of a node. And then we could learn what is the importance of centrality. So that would be interesting, actually.
Because I think if you did that, you would connect it more to at least where the sociology of networks has gone the last couple of decades. And if you can link it up with concepts like centrality and other measures, I think then you might be able to inform that literature in new ways and impactful ways.
Yeah. Well, I wouldn't say that the field has completely moved to these global things, because there really is this connection between global and local. When you make a decision who to become friends with, it's always a local decision, because you only see what's going on around you. And somehow this gives rise to a global behavior.
Right, but I'm thinking, if you think about the sociology of networks, the last couple of decades has gone to this structuralist position where the only thing that matters is the structure of the network, and who cares about the content, including language or text and so on. That's obviously gone to an extreme, right?
Yeah.
I think with your models, you have an opportunity to put back in the content such as text, while keeping also the network structure, kind of merging the new and the old of those networks.
I think the very new
that's
is
a very interesting avenue for research.
I totally agree. And I think the very recent developments are starting to realize that and to go away from this purely structuralist point of view. Yeah.
Okay, so thanks for a great talk, Bob. So I want to see if you could reflect a little bit on this choice you're making, and that many people make when they do sentiment analysis, about treating that sentiment as being essentially a binary value. And this is especially complicated when we're talking about the attitudes that people have with respect to other people. And I think even in the case where you're relaxing that assumption in terms of the hinge loss, it's still clear that it's still almost a Bernoulli random variable. It definitely has a value of either 0 or 1, but you just have uncertainty about which of those 2 true values it actually is. So I wonder, in reality, of course, even if you treat it as being a single-dimensional thing, there are still gradations that people feel about liking people more or less. And there are also, of course, other just complete many different kinds of categories that people can have with respect to each other. So social relationships and
Yep.
familial ones that aren't necessarily even comparable on the same scale. If you wanted to build a model that included relationships that are either gradations or are categorical memberships, how could you still use balance theory to do that?
Yeah, this is a great point. I think the real problem is not the binarity, because that's, as you said, that's relaxed in this model. The real issue is the unidimensionality, right? That there might be different types of, even if we talk about the same two people, we might relate to each other across many different dimensions. In a professional dimension, a personal dimension, I might trust you but not like you, things like that. And I believe that our model would accommodate that, because, so I motivated everything based on this intuition from structural balance theory. But really what's going on is that we're learning different weights and penalties for all the different triangle types from the data in a machine learning fashion. So even this model that I showed you really learns that plus, plus, plus is the really important one that you should get right. And minus, minus, plus is, while it's equally predicted by structural balance theory, there is a lower penalty for not having that in our model, because it's learned from the data. And I think that if we had a data set that had these multidimensional relations between people, then all these things would still apply, because the method would just pick up on the types of motifs that are prevalent in the observed part of the network. So in fact, running this type of method on a data set might even inform the sociological aspects and might help us understand what are the equivalents of structural balance theory with respect to the, say, the multidimensional case. What's really an issue is finding data for that. So even the data sets that are used here are a couple of the few data sets that really have the signed network explicit. I would argue that most social networks are really signed implicitly, but the data is just rarely public. So for example, on Facebook, you only see positive connections. And you could say, well, the absence of a connection is negative, but that's not going to be the reality. Sometimes it's just not explicitly labeled. And that's going to be a real challenge for running these types of methods on the multidimensional case. So one interesting direction would be to think about ways to collect labeled data sets, labeled networks. Sorry? Okay, okay.
Thank you. That was fascinating talk. I could ask a lot of questions, but I'm just curious to follow up on your next work. It seems to me in terms of humor, there's an element of context that's required. In other words, you have to know something about who Margaret Thatcher was to be able to get the humor in that, although there's some jokes that aren't contextual, perhaps. And the other is cultural, and I'm wondering, given your linguistic background and combining that with computer science, if you think that some types of humor, such as satire and irony, don't necessarily transfer as well, say, to German or perhaps to some other, and there's some types of humor, or what makes something humorous in terms of its juxtaposition of elements you wouldn't expect, that varies if you take this research another step.
Yeah, well, nothing humor-related translates to German. No, but it's a great point. So there's a vast body of literature in anthropology, for example, that looks at cross-cultural differences of humor, and they're really vast. But there seem to be some elements that there is some nearly physiological basis of humor that manifests itself across languages. But I think even the intra-cultural part is really hard enough, and that relates to your first question. What about the culture? What about the backgrounds that you need to have or the background knowledge that you need to have to deal with these types of things? And yeah, that's a huge point. And I think that's why in the short term, having a human in the loop will be crucial, because the human has all that background in them, right? So if we say in this case, we started from the serious headline that Margaret Thatcher's ashes were scattered over the Atlantic Ocean. Then if I could give this to, say, 100 humans, and I ask them to identify a phrase in that headline that could be changed in order to potentially transform this into something funny down the road. So I get these 100 opinions from people, and then I might do some majority voting or something, and then I might give the top candidate to the next human and ask them, change this towards something that plays with the fact that removes the respectfulness from this statement or something like that. And again, send it out to 100 humans and collect the answers and so on. So those are the ideas, but the idea would be that the human in the loop would have all that common sense and background knowledge that would be necessary. It would be very hard to encode that in a computer, but what the computer is much better at is to maintain maybe the high-level steering of what's going on. And another approach would be kind of at the very different end of the spectrum, would be more like a data mining approach. Imagine that we back up our method with all the knowledge that's out there on the web, and we have resources like Freebase and so on that expresses what job Margaret Thatcher had, who she was related to, and all these things. So I think if we use that as background knowledge, and treat the problem, bring this data mining perspective into the problem, then that might also be one way forward. That being said, that's why I suggest it as a long-term research project, because it's super challenging, and I think a lot of different things will have to be solved on the way.
Last question. Going back to the first piece of work, the linking in Wikipedia, it could be a question that having all the hyperlinks in the text is more distracting than helpful. I mean, it's useful if you really want to explore that thing. And an alternative, though, might be to have a section at the end of recommended reading, say, for example. So I guess my question is, have you thought at all about the attention model in these recommendations, sort of the more psychological angle on that when doing this sort of work? Or what is the basis for just assuming that you should go along with one link per page? And also a related thing that occurred to me is the model had a sort of a zero-sum aspect to it, sort of assuming that there's only the given number of people who are using Wikipedia in the model, and not that if the model were more successful, that it might draw more people to Wikipedia than are already there, that there was only a limited amount of attention in the entire system. And perhaps if it were less distracting in some sense, more people would use it.
Yeah, that's an interesting point. And there's actually this long-term debate among Wikipedians why shouldn't we just make everything black in the page, basically? So remove all the visible links and just put a link on everything, so you could click every word. But there is a conscious, the communal decision is to not have that, but to clearly mark the things that would help you in terms of getting more context for the page. So that's just kind of a constraint that we have to work with. And regarding the assumptions that we make about the attention model and so on. So we did not do a lot of qualitative work here. What we did is we quantitatively looked at the data, and we looked at what happened. Let's say we take the same article and we track it over time. We track it over 3 months, and then some articles will have, there will be a delta in terms of the number of links. So some articles will see many links added. Most of them will remain largely constant, and some articles will see a decrease in the number of links. And then we look at how does that affect the number of clicks that the average person makes out of the page before versus after that delta change. And what we find empirically is that basically nothing changes. So if you add more links, that doesn't mean that people will click more links. And that's what we took as justification to have this model of attention in there. No, that's just the K parameter, you mean? Sure. But the idea is that you can compute a probability that the user will click one of the new links from that page, and then you get the total sum by. So that's the probability. Then if you multiply that with the number of times that the page was visited, then that gives you kind of the out volume from that page. And if you sum that over all pages, you get the total out volume. But it's not bounded. If you no. Just within a page, it's normalized to sum to 1. Yeah.
I have 2 questions. One is how constrained are kind of the results that you're seeing to the context that, the folks who are doing the initial link selection on Wikimedia have already had all this training about what things should be linked, and so just, how constrained are the insights that you're getting from this? What would you think in thinking about their translation to other areas where you don't necessarily have that same enormous effort to kind of create a culture that has some shared idea about what to link to? And then I'm just at a qualitative level, did you or have you or are you going to go and ask people, well, if there is this limit to the number of links people make, and yes, it's nice that there's some correlation between the things that the algorithms identified and things that they've identified, are those actually the most important ones, or these things that people aren't linking on because they're linking on these other things that might be maybe of less value? I don't know, but they're more like candy. And so are you doing that qualitative piece? Because it seems to me that it's the fact that there are this shared set is interesting, but it doesn't necessarily tell me that it's the right set. So
So the first question was about the generalizability, basically, of this approach. So I talked only about Wikipedia here, but in the paper, we also run this method on another website. That it's just one that we happen to have access to because it's maintained by Stanford. It's SimTK, it's called. It's a website for biomechanics engineers, and they publish their code and project descriptions and so on there. And so we just used that because we had access to the logs, and it works nice there as well. So we also have these, if you remember that cigar-shaped plot, so we see similar things there.
Do you view those as similar sorts of intentional communities that have a shared objective?
Yeah, there are huge differences between all those different communities, because Wikipedia is an online encyclopedia, and that SimTK site might still be similar because people come to look things up, but you might have very different websites. So clearly that's something that needs to be considered from the fundamental perspective. There are also implementational things that will make it harder to run this method on other websites, because one really nice thing with Wikipedia is that every page is about a crisply defined topic, and it's even explicit in the name of the page. If you go to an arbitrary web page, that might be much less the case. It's this mumbo jumble of where something talks about a mix of topics, something talks about nothing at all, and something talks about a crisp thing. So that will make it much more challenging, because then you would basically first have to run topic modeling and things like that to even represent what this thing is about. The other thing is identifying the anchor text is very easy in Wikipedia, because you have this huge set of statistics. You can just see at Wikipedia right now what are the anchor texts that link to each of the pages. And in general web pages, you might not have that so much. So the anchor texts might be much less rich in terms of the content that they have. So that's another thing. So there are definitely challenges. But I think the approach is appropriate in the sense that it directly captures the user's behavior. Whereas if you look at many of the other approaches, they only look at, say, the graph structure, or you might look at the textual contents of pages and then find which pairs are similar there. But I think it's a strength of this that we look at the behavior, because I could, for example, run this on Chinese Wikipedia, don't understand a word, but still I would conjecture that the results would be similarly good. So I would see that as strength. But you had a second question, and that was, let's see if I can remember it.
Just whether or not you've talked to people, the editors, about the ones that don't.
Oh yes,
yeah.
right. So that's a question of recall. Basically, would there have been other good ones that we didn't get? And that's always much harder to evaluate because you would need a ground truth set of the relevant ones to evaluate that. Precision is much simpler because you can just take the thing that you have and ask someone, is this good or bad? But just by comparing to what though?
Well, the things that the editors chose that
well, I'm going to suggest we take this offline because a lot of people have to go and it's 2 o'clock. And let's thank our speaker, Bob, who's been up here for an hour and a half.